Hi everyone, we're going to look at how to do explicit to recursive for geometric sequences. So any recursive relationship will always look like this. Next equals the current, and it's either times something or plus something if it's recursive, or if it's geometric, or if it's arithmetic. In this case, it's geometric, so it'll be times something, and there'll always be a starting point. If you don't tell me where to start, I don't know how to produce your sequence. Giving me some starting value like 10 and then multiplying by 3, I can produce any sequence value I like just by starting at 10, doing times 3 over and over again. So that's how we define a sequence recursively, and then for geometric it has multiplication in there. So for these we're given explicit formulas here in either way. So the left side here is how you typically would see it on the Regents, where it has the reference sheet where it's a1 times r to the n minus 1. But the one on the right is what we're typically used to for exponential functions, where it's y equals a times b to the x. So the 4 would be a 0, and then this 24 would be a 1. That's the big difference here, besides the n minus 1 and the n. And you have to know which one's which. I think it's a little bit easier to think about what we're used to, which is the y equals a times b to the x, using our y-intercept. Usually that's easier to work with and you make less mistakes. So let's use that. Let's find some terms here of this sequence. So our first term, a1, would be 4 times 6 to the first, which would be 4 times 6, which is 24. So to make a little table out of this, we could do n and a sub n. So our first term is 24, and our second term, a2, would be 4 times 6 squared, which would be 144. Since we just multiplied by 6 here to go between those two, that's a relationship, since that's the amount we'll be multiplying by every single time, because it's the base of the exponent. So working backwards to find the y-intercept, we already know what it is because it's right here. 4 would be a 0, because that's times 6. So then to write our recursive sequence here, we would just do next equals now format. So the next one, an plus 1, would be the one before it, an, times 6. And we're going to start at the first term, which was 24. So a1 equals 24. So the top part would be when n is greater than or equal to 1. You would use that formula to get a2, a3, etc. Or we could say an is the one before it, an minus 1, times 6, again starting at 24, and this would just be for when n is greater than 1, or n is greater than or equal to 2. That would work either way. You might see it either way in a multiple choice question. You just have to know they mean the same thing. Don't get caught up on the next now here. This is the next one if this is the one before it. They both really represent the exact same thing. For the next one here, very similar. We want to just figure out where are we starting, how are we moving. So we can make a little table, x and f of x. So our first term and our second term would be good to know those. So f of 1 would be 9 times negative 3 to the first, which is negative 27. F of 2 would be 9 times negative 3 squared, which would be 9 times 9, which is 81. So we've multiplied here times negative 3 in order to go from negative 21 or negative 27 to 81, which is of course right there. Our negative 3 is what we're multiplying by since it's the base of the exponent. So that would be our r in the formula, which we're multiplying by, the factor. So our recursive formula would just be f of x plus 1, the next term is the one before it, times negative 3, starting at our first term, which is negative 27. And this would be when x is greater than or equal to 1. Or we could say a little bit differently. We could say f of x is the one before it, f of x minus 1 times negative 3, again starting at negative 27. And this would be when x is greater than 1. Either or, they both say the same thing. It's just next equals now times negative 3, starting at negative 27.